Now to tonight's special report and rare access to an incredible experiment looking for the origins of the universe. Inside an unassuming mine in central Japan, scientists are hunting for neutrinos, ghost-like particles that are smaller than an atom and float through almost everything. They travel at the speed of light and explode out of nuclear reactions, the sun and dying stars, giving us clues about the Big Bang. The science from these Japanese experiments has already won 2 Nobel Prizes, and those involved are hoping for a third. North Asia correspondent Jake Sturmer takes us inside the machine, which hasn't been opened for more than a decade.
If you want to find the most elusive particles in our universe, the trick isn't to look up, it's to go down. We're in the middle of Japan, heading 2 kilometres inside Ikano Mountain, looking for the building blocks of our universe. This is the Super Kamiokande, a $100 million water tank inside an old zinc mine. The experiment is searching for neutrinos, tiny particles like the ones that come from our sun or the heart of massive exploding stars, supernovas.
We would like to understand how those stars explode and how they work. And one of the best ways to do that is through their neutrino emissions. Therefore, studying neutrinos is an indirect but a definite way to explore our own origins.
When supernovas explode, they spread crucial elements, including carbon and oxygen, throughout the cosmos, the exact elements needed to create the universe we live in.
And we would not be alive without supernovas, most certainly. Supernovas are the best source of neutrinos in terms of the most efficient generation.
But catching those neutrinos isn't easy because very little can see or stop them. That's why you need a tank like this, lined with what look like giant light bulbs. They're known as photomultiplier tubes, or PMTs. They work like light bulbs in reverse. Instead of converting electricity to light, they convert light to electricity.
Here we have 11,129 PMTs. It's really very sensitive photosensor.
So one of these could see a flashlight on Earth from the moon?
Yes, right.
Wow. It's hard to truly capture the scale of this experiment. It's quite disorientating being in here, but to give you some sense of the size, you could fit the entire Statue of Liberty inside this tank.
Normally this would be full of water. When neutrinos slam into the liquid, that's when the giant tubes can see the collision. The water has so many impurities taken out of it, it actually turns corrosive. Given long enough, it can even dissolve metal, something scientists learnt when they dropped a hammer in the tank.
A few years later, we were servicing the detector and we found the hammer. And there was a chrome shell, just wafer thin, and the interior was hollow. The water had eaten all the metal out of the hammer.
Professor Mark Vagans has been leading an upgrade to improve the power of the experiment.
Okay, this is my secret underground lair.
He built his own mini Super K to prove that adding an element called gadolinium to the water can make it much more sensitive.
So this is the gadolinium sulfate. This is what we're going to put into Super K, and this is what makes the magic happen. So we will be able to see 35,000 times further into space.
It's now a race to get the machine repaired and refilled as soon as possible, so it's ready in time to spot the next supernova neutrinos to hit Earth. But even if it doesn't see any, that's a win for science too.
Neutrinos are the lightest things we know about. So if these things decay, that implies new physics, new particles, a whole new underlying world. And so essentially, as I say, it's really a case where you can't lose. Either you measure something everybody wants to measure and learn from, or if you don't see it, then you have a whole new world opening up of discovery.
A new world and perhaps a third Nobel Prize. Jake Sturmer, ABC News, Kamioka.